Section 8.2, area of a surface of revolution. Let's begin with a definition of surface area. When f is positive and has a continuous derivative, we define the surface area of the surface obtained by rotating the curve y equals f of x on the closed interval ab about the x-axis. If we're following these rules, where we have y equals, in other words, it's in terms of x, we're rotating about the x-axis. In such case, our formula is s equals our integral from b to a of 2 pi f of x, that's our function, square root of 1 plus f prime, our derivative, squared dx. And similarly to arc length, we may change the variable we're working with. If that is the case, we are also changing the axis for which we're rotating the surface. So to find the surface area, when we have a function such as when it's in terms of y, such as x equals f of y, and we have some bound for c less than or equal to y less than or equal to d, our surface area is the integral from d to c of 2 pi y of our function y, square root of 1 plus our derivative in terms of y squared dy. Let's go ahead and do an example. The curve y equals the square root of 4 plus 4 minus the square root of 1, negative 1, less than or equal to x, less than or equal to 1, is the arc of the circle. X squared plus y equals 4. Find the area of the surface obtained by the rotation of this arc about the x-axis. The surface is the portion of the sphere of radius 2. So it's telling us the whole circle is the equation x squared plus y equals 4. But we only want this small portion. So don't let all these different equations kind of fool you. All right, so we have our formula right above. First thing, we need to go ahead and write our derivative. So our equation is in terms of x, we have y equals. Let's go ahead and find our derivative. So y prime is equal to, we have to use chain rule, 1/2 4 minus x squared of negative 1/2 times the inside derivative, which is just negative 2x. Our 2 and 1/2 make 1. And we're left with negative x divided by the square root of 4 minus x squared. Okay, so now that we have our derivative, let's go ahead and use our formula. So we have s is equal to our integral of 2 pi, and then we want our function, the square root of 4 minus x squared, and then we want our radical of 1 plus our derivative squared. So in this case, we're going to write negative x over the square root of 4 minus x squared squared. And we're working with our x's, so we have a dx. Now our bounds. We see that we're working on a closed interval from negative 1 to 1, so it's from 1 to negative 1. All right, that's our formula. From there, we just go ahead and try to integrate and simplify as we work along our integrand. All right, so on the inside, we see we square that derivative so that we have, and we can also move this constant to the front, so that we have 2 pi, our integral from 1 to negative 1, of the square root of 4 minus x squared times square root of 1 plus that negative x squared turns into positive x squared. And we have our radical squared, so we just have 4 minus x squared. Let's go ahead and get a common denominator and combine like terms and simplify so that we're left with 2 pi of 1 to negative 1, the square root of 4 minus x squared times, and we're left with 4 minus x squared plus x squared over 4 minus x squared. We just got a common denominator. We see our x's add to make 0, and we're left with square root of 4 minus x squared times 4 over 4 minus x squared. Okay, let's go ahead and apply the radical to the numerator only. That will give us 2. Over the square root of 4 minus x squared dx. And something very cool happens here. Not to say that's going to happen every time. Every integral will be from case to case, and we're going to have to rely on all of our past knowledge of integrals to simplify. This one worked out super nice. We see that our denominator and our numerator divide to make 1, so that we're just left with 2 pi from 1 to negative 1 of 2 dx. 2 is a constant, we can just go ahead and move it forward. So we have 4 pi from 1 to negative 1 dx. You can write 1 as a placeholder. The integral of 1 is just x. So we're left with 4 pi of x. And we're saying x goes from 1 and x goes to negative 1. All right. So we have 4 pi, and I have 1 minus negative 1. So that we're left with 4 pi times 2, which is just 8 pi. Not so bad of an example. This one was fairly simple in terms of integrating. All right, let's go on to our next example. Example 2. The arc of the parabola y equals x squared from 1, 1 to 2, 4 is rotated about the y-axis. Find the area of the resulting surface. All right, so we see it's just a part of our parabola. From 1, 1, which you see here, all the way to 2, 4. We want the enclosed area of the surface, so just the surface. All right, so we have options. Let's go back into our beginning formulas. We saw that we have options. We can rotate along our x-axis or y-axis, and all it does is we're changing our arguments in terms of x, so solve for y, so everything's in terms of x. I know it sounds weird, right? We're solving for y, so it's in terms of x, or we can go ahead and solve for x so that it is in terms of y, and we can integrate for y. Now, the thing that we have to keep in mind as we're changing the rotation is our values for which we integrate under. So this problem here, example 2, jumping back to example 2, gives us a lot of liberty. It gives us liberty mainly because we have a function which we can easily change from x to y, and we have both points, both x and y coordinates of our points. So this problem is really up to you. Do you want to work with x and integrate for dx, or do you want to work with y and integrate with dy? Now, since we just did an example where we worked with x, I'm going to go ahead and work with y. If you work with x, this problem, so you can try on your own, this problem is fairly simple if you integrate using working with x. It's not any harder. So you can do it. Working with y, it's not any easier either. They both require you to use substitution. All right. So if I want to work in terms of y, I need to solve for x. So we have y equals x squared. If we solve for x, we have x is equal to the square root of y. All right, now we need our derivative, which is something we'll use in our formula. So we have x prime is equal to 1/2 y to negative 1/2, which is just 1 over 2 square root of y. So we have our derivative and our function in terms of y. Let's go ahead and use our formula. So our formula reads s is equal to our integral from d to c of 2 pi f of y square root of 1 plus f prime of y squared dy. So the only parts we really need to input are our formula or our function derivative, and our limits for our integral. Let's go ahead and do that. So we have s is equal to, now we want our y. So we have our y1 and our y2. So it goes from 4 to 1 of 2 pi. Our function in terms of y is square root of y times the square root of 1 plus our derivative squared. So we have 1 over 2 square root of y quantity squared dy. Not so bad, right? Okay, that's our setup. And if this were like an exam or a quiz problem, this would probably be like a good 2/3 of the points. Now from here, it would just be a matter of integrating and evaluating for our endpoints. Okay, so we have that quantity squared. Let's go ahead and clean that up so that we have, let's move those constants forward. 2 pi from 4 to 1 of the square root of y times the square root of 1 plus 1 over 4y dy. Okay, now because they're multiplying and they have the same radicand, by your rule of radicals, we're able to multiply the insides because they have the same index, meaning they're both square roots or cube roots and so on. So we have 2 pi from 4 to 1 of the square root of y times 1 plus 1 over 4y dy. Let's distribute that y. So that we have y plus 1 over 4. Those y's cancel, right? Okay, from there, let's go ahead and well, from here, what I did the first time, took several times, I integrated using u substitution, but that 1/4 proved to be very problematic when simplifying. Now, I can get rid of this 1/4 because I have this 2 here. Remember, 2 is the same as the square root of 4. So I can work inside my radical as a square root of 4. So that we have, so again, we're moving in this 2 into the radical. So that we have pi from 4 to 1, the square root of 4 times 1 plus 1 over 4 dy. And we did that to make that 1 over 4 become an integer. So we have pi from 4 to 1 of 4y plus 1 dy. And it just, I mean, it's not necessary if you're just like quickly integrated something that I, for one, would look over, but it's really helpful. Okay, let's go ahead and integrate using u substitution. So if we go ahead and let u equal our inside portion, so we have 4y plus 1, then our partial derivative du would just be 4 dy. So we have our dy, we need to multiply it by in 1/4 to cancel that 4. So that we're left with 1/4 pi integral of u du. Now if you want to not go back and plug in, replace that u value with what we said it is, you can always label your values or change your bounds. So we have y is equal to 4 and y is equal to 1. Let's go ahead and replace that. So we have u is equal to 4y plus 1. We're going to go ahead and let y equal 4, so that we're left with 4 times 4 is 16, plus 1, 17. So now we now have 17. And we had y equals 1. So we have u equals 4y plus 1, and y equals 1. So we have 4 times 1 plus 1, we get 5. That way we don't have to go ahead and replace the u after we integrate. All right, so we have 1/4 pi of 12 to 5 of the square root of u du. Let's go ahead and integrate. So we have 1/4 pi, and we have u to the 1/2 power plus 2 over 2. We get 3 over 2. We divide by our new exponent, which is the reciprocal, 2 over 3. And we're going to plug in the values u equals 12 and u equals 5. So we have 1/4 pi of, let's go ahead and factor out that 2 over 3 constant, so that we have the square root of, I think I misread my own writing. We said it was 17, and I think I somehow changed my 17 to a 12. So let's fix that. 17. So we have the square root of 17 cubed minus the square root of 5 cubed. All right. So that we have this right here gives us 2 over 12, which is 1 over 6 pi. And we're left with 17 square root of 17. There's 3 copies of 5. 2 can move forward, so we have 5 square root of 5. And that's our answer. Not so bad. Now, I was under the impression that you had maybe seen in your first calculus course how to change your bounds if you wanted to, if you didn't want to go back and like plug in the value of u. I'll be more careful about showing every single step in our video notes. All right, example 3. Find the area of the surface generated by rotating the curve y equals u to the x when x is bounded from 0 to 1 about the x-axis. All right, so this was kind of leading us to work with x, mainly because We're working with a function where while we can solve for x, it's much easier to leave it for as it is, and we're only given the x bounds. But we can always find out the y by plugging in the x. So never think that you're solely committed to rotation about one axis. You can always interchange. But let's work with about the x-axis. So if y equals e to the x, therefore our derivative y prime equals e to the x, right? E to the x is its own derivative. So let's go ahead and plug this in. So our formula for our surface area is x is equal to our integral. Our bounds are from 0 to 1, so 1, 0, of 2 pi. And then our function. Our function is just e to the x. The square root of 1 plus our function's derivative squared, which again, in this case, it's e to the x squared dx. Okay. If you like to, you can always start off by moving those constants out of your integral so that you have less things within your integral. All right, so we have 2 pi from 1 to 0 of e to the x square root of 1 plus e to the 2x dx, right? In case you're wondering why it's e to the 2x, it's one of those exponent rules that says if I have a to the x to the y, the same as ax times y. So those end up just simply multiplying. Okay, we see here that u substitution will work really nicely. So let's go ahead and start with u substitution. So with u substitution, okay, I don't have too much space. So if I use u substitution, and using the inside as our u is not ideal because when we take the derivative of our exponent, we still need another x to account for it, which we don't have. So let's let u equal e to the x. Therefore, our du, our partial derivative, is e to the x dx, which we have, right? So we have our u and we have our du. Let's make that replacement. So we have 2 pi from 1 to 0 of the square root of 1 plus u squared du. We're still in a pickle. We still can't integrate because we have our variable squared without having a derivative form within our integral. So we have to rely on our trig substitution for integration. All right. So second step from here is trig substitution. All right, let's look back into section, I think that was section 7.3. Look back at your chart. Yeah, 7.3. And we see we have a constant plus a variable squared. So we have a plus that tells us that we should have a, or have that substitution be a equal tangent theta, where a is your constant. In this case, our constant is 1. So it'll just be 1 tangent theta, or just tangent theta. Our, and I already made a mistake. We're not working with x, we're working with u. So we're going to let u be tangent theta. Therefore, our derivative will be secant squared theta d theta. Okay, with that substitution, let's go ahead and replace our u with tangent theta. So let's only work with the, well, I think you've seen it enough. So that we have 2 pi integral from 1 to 0. Inside our radical turns into a secant theta. And our du is secant squared theta d theta. So that we have secant cubed theta d theta. Now to integrate this, we've seen as an example and it's actually an identity. So our integration by your identity, this secant cube theta, our integral is 1/2 secant theta tangent theta plus the ln of secant theta plus tangent theta. And we have to plug in those values when x is equal to 1 and x is equal to 0. And let's not forget our 2 pi. Of course, we see that 2 and that 2 will cancel off. Now we have to go through the trouble of working backwards to find these values of theta. Okay, let's work backwards. So our second to last step was trig sub. Let's go ahead and use trig sub to find the values in terms of u. Okay, so by trig substitution, we said u is equal to tangent theta. So let's draw a triangle because we also need to find secant, right? So if we draw a triangle, 90 degrees, we need a theta. Tangent is the same as opposite over adjacent. So we have u being opposite. We can let 1 be adjacent. So our hypotenuse is u squared plus 1 squared. So plus 1. Therefore, secant theta. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So we want hypotenuse over adjacent. Hypotenuse is square root of u squared plus 1, and our adjacent is 1. So it's just the square root of u squared plus 1. Let's make those changes so that we have pi of, instead of secant, we'll write square root of u squared plus 1 times tangent. Tangent is just u plus the ln of, not secant theta. We said secant is the square root of u squared plus 1 plus tangent. Tangent is u. All right. And we have x is equal to 1 and x is equal to 0. We want it in terms of u, but we already have a substitution for u, right? We said that u is equal to e of x. So let's make those changes. When x is equal to 1, u is equal to e. And when x is equal to 0, u is equal to 1. So we can change that to an e and change that to a 1. Let's go ahead and plug in 1 and 0. Now, it seems as though I've run out of space, but I highly think that you're able to continue from here. Your final answer will be pi of the square root of e squared plus 1 square root times e plus the ln of the square root of e squared plus 1 plus e minus the square root of 2 plus the ln of the square root of 2 plus 1. In case you're wondering, it didn't combine. So that would be when you plug in 0, that would be when you plug in, when you plug in 1 and when you plug in e. Alrighty. That's it for section 8.2, area of a surface of revolution. Thanks.